Hello and welcome back. We have been studying the Gaussian elimination method, which is also known as GEM or GEM for short. And we already saw that when one of the pivot elements AII is 0, then the Gaussian elimination method cannot be performed. And so we have to make some changes. So let's study further on the same theme. Um, we start with sharing the lecture slides. I hope you can see the slides now. All right. So we have already seen that in GEM, a row interchange was needed when one of the pivot elements AKK is 0. And this row interchange has the form EK replaced by EP. So EK and EP are switching, where P is the smallest integer greater than K with APK non-zero. What happens is that whenever AKK is 0, we look at the kth column below K. So we will look at A K plus 1K, A K plus 2K, and so on. So there will be a P which will be after K, but the first one where you get that APK is non-zero. So AKK is 0, you may have that AK plus 1K might also be 0, the next one may be 0, so you choose the first one which is non-zero and then switch these two rows. This is what we do, and what one has to do is to do this kind of operations even when your pivot element is not 0. So that is what we are going to talk about today. Okay, so there is a round of error that can take place, and therefore we have to perform row interchange operations even when the pivot element is not 0. So what happens is that if you have AKK which is not 0 but it's very small in magnitude compared to AJK, okay, then the magnitude of the multiplier MJK, which is AJK upon AKK, will be much larger than 1. This is what will happen, meaning suppose you start with AKK, the pivot element, it's not 0 but it's very small, and then there is an element below that in the same column somewhere which is slightly bigger than this element, or let's say it's comparatively quite big compared to this element AKK. Then when you are making changes to J for eliminating the variable xk, you will multiply by this number which we call multiplier, which is mjk, which is given by the ajk that you have, divided by akk. Now ajk is already large and akk is very small, so by dividing a large number by a small number you are going to get a very large quantity. And then round off error introduced in the computation of one of the terms AKL. You may already write your elements using some finite digit arithmetic, and there may be a rounding off error. That error will be multiplied by this large MJK. That is what will happen. Okay. And this will compound the original error because you have MJK which is large, and then in the jth column you will look at various numbers that you have, and the jth row you will have some numbers, kth row you will have some numbers, and you multiply by that AKL, kth row, lth column element by MJK, and you will then subtract it from the jth row, and that might make things go haywire if there is this round of error. Okay, so let's so there is, of course, you will have to divide by this small quantity even when you take the backward substitution. So while performing this backward substitution, you will need to compute for xk. And how do you compute for xk? You will look at the ek, which is kk xk plus a k plus 1 xk plus 1 dot 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 equal to bk, and then you will subtract from bk, or which is also known as a k plus k comma n plus 1 when you are writing the augmented matrix. You will subtract the summation of the previous terms. and then you will need to divide by AKK. So for a small value of AKK, this any error in the numerator will dramatically increase when you are dividing by AKK. This is what will happen. For instance, we will see an example that for even for small systems, round of error will dominate the calculations. So for instance, let's consider this system. You have two equations, E1 and E2. And E1 has the pivot element which is 0.003, which is a small number compared to the next entry, the second equation coefficient of x1, which is 5.291. So roughly the A11 is 1000 times smaller than A21 as a factor. Okay, and the correct solution is x1 equal to 10 and x2 equal to 1. Okay, that's the correct solution. So for instance, here if you put x2 equal to 1, it is just 59.14 and you multiply this by 10. So instead of 003, you will have 0.03, which when added to 59.14 gives you 59.17. Similarly, this is 6.13 and here you will have 52.91 and the subtraction is indeed 46.78. Okay, so we will see what happens when we apply the Gauss elimination method as it is. The first pivot element is small and then M21, which is obtained by 5.291 upon this 0.003. This is 1763.66666. So when you use 4-digit rounding method, you will get 1764. Okay, and now what, this is our M21 rounded, and then now we have to perform this operation E2 minus M21 E1 going to E2, and then the appropriate rounding will give you this system where your first E1 of course will not change, but the second one changes and it gives you minus 1043.00 x2 equal to minus 1044.00. x2 was supposed to be 1, so both the constants should have been the same, but now they are not same. So instead of exact system, this is the system that we get, and the disparity in the magnitudes of M21 A3 and A23 has introduced this round of error. But we have not yet seen the propagation of the error. The error is still going to propagate further because we are going to use the backward substitution. So backward substitution will tell you that x2 is 1.001. You know, I told you that first equation has not changed. In fact, I can just put equality here instead of approximation sign. Second one had changed, and although it has not changed much because the equation solution is 1.001, which is roughly equal to 1, but because of this small pivot A11, which will have to be divided by, when you compute the value of x1, we are going to get that x1 is approximately 59.17 minus 59.14 into this value, which is now slightly bigger than 1. Therefore, the numerator is going to become a negative quantity, and then you are dividing by a very small number. Therefore, in the rounding, you get the answer to be minus 10, whereas your correct answer is equal to 10. So this is what has happened. So this has, the error is a small error, which is 0.001, which has been multiplied by this big number. So the error, which was 1.001 minus 1, which was 0.001 in the x2 value, that has now magnified by the division by the small number in the computation of value of x1. So roughly a factor of 20,000, that's the error that we have now got, and that has completely ruined the approximation to the actual value, which is x1 equal to 10. Of course, you know, you may say that this is an example which is contrived. This is an example which is cooked up. Indeed, that is true. This is an example which is cooked up just to tell you how bad these things can go, but it does give you an idea on how the round of error can alter the results. So then what we do, is that we go to partial pivoting. So for very large systems, it is much more difficult to predict in advance when this devastating round of error might come. It is very difficult to predict it. So to avoid this problem, pivoting is performed by selecting an element APQ with a larger magnitude as the pivot. Okay, and interchanging the kth and pth rows. So you have the kth row, assume that x1 up to xk minus 1, those things are dealt with. So you have the diagonal entries for the first k minus 1 diagonal entries, and all the things below them are 0. And now we are looking at the kth place. So what one does is that in the remaining n minus k cross n minus k matrix, look at the largest magnitude element. And if that is in a particular row, then you replace your kth row with that particular row. But because now the larger magnitude element has gone to a further place, so you will have to also interchange the kth and qth columns if necessary. But remember that when you are interchanging the kth and qth columns, you will have to change the variables also. So that is something which has to be done slightly carefully. So far, what we have done is only the row operations. We have not touched upon columns. We have not interchanged columns. And so whenever we are doing row operations, we are keeping the variable matrix x1, x2, x1, x2, xn as it is. And we perform the row operations on the constant vector also, the b1, b2, bn. That is what we have been doing. Okay, but if you are changing the kth and qth column, then you will have to change the xk and xq variables also. So this is something which is a bit tricky. So what one does instead is to look at the same column below the diagonal and then look at an element which has the largest absolute value. Okay, so we will not be changing columns now, but we are looking at that kth column, which is the column that we have to concentrate on. And instead of taking your AKK, you look at AKK, AK plus 1K, AK plus 2K, and so on up to ANK. Choose an element which has the largest absolute value in the modulus sign, the largest value. Specifically, we determine the P bigger equal K, the smallest P, such that the APK is the maximum for AIK, where I runs from K to N. Okay, and then you perform the operation EK changing to EP. This is what we do. And now there is, of course, no interchange of columns is needed. Okay, so now what we are doing, let's look at our system once again. We had this system where E1 was 0.003, x1 plus 59.14 x2, which is 59.17, and then you have E2. But here when you look at the first column, the A21 has larger magnitude than A11 in the modulus sign, right? So using partial pivoting, what we do is that we want to find maximum of mod A11 and mod A21, which is mod A21. So we switch these two entries. So we perform E2 switched with E1. And what we get is the same system, but our equation E1 is now the earlier equation E2. And the E2 equation is the earlier equation E1. The solution set is the same. Solutions are not going to change. And now we apply the Gaussian elimination method. So the multiplier is now A21 upon A11, it's going to be the reciprocal of the earlier one. So it is now 0.005670. Earlier, we had divided by this number, and now we are multiplying by this number. That is the difference. So by effecting the E2 minus M21 E1 and replacing that in place of E2 will give you the system. E1 is not going to change. E2 becomes 59.14 x2 approximately equal to 59.14. This will now give you the correct answers, that x2 is 1 and x1 is 10, because the second equation is giving you x2 equal to 1. When you put it back in the first equation, first equation has not changed. So it should give you the correct value of x1 equal to 10. So each multiplier in the partial pivoting algorithm will have magnitude less than or equal to 1. Because what we are doing is the following thing. We start with your matrix A, look at the first column. We will look at the pivot A11, but instead of looking at A11, we look at the first column, see which entry has the maximum magnitude, replace that, put that row in place of the first row and put first row in place of that row. So now your A11 has in magnitude largest entry among the whole first column, and therefore when you compute the multiplier, you will be dividing by this largest entry to all the other entries, and therefore the multiplier MJI will have magnitude less than or equal to 1. There might be two entries with the same magnitude, the maximum one. Therefore, there might be some multiplier which might be equal to 1, but otherwise it will be less than 1. Okay, so life would have been really good if this had worked everywhere, but even this strategy sometimes is not adequate. So let me try to explain what goes wrong. So for instance, we are now considering this linear system. If you remember carefully, this is the same as our earlier linear system, except that we have multiplied the equation E1 by 10 power 4. So we had 0.003. That 0.003 has now been made into 30. So we multiplied it by 10 power 4. The 59.14 has become 5,91,400 and 59.17 is now 5,91,700. So this is what we have, and the partial pivoting procedure with the same that we have applied, partial pivoting and 4-digit rounding will give us incorrect results. So let's see what happens. We are looking at the very first example, how we got the incorrect results, remember? And in the when we applied the pivoting without partial to the original equation, then we had got the incorrect result where x1 was minus 10 and x2 was 1.001. Okay, we are saying here that if you now change even by this multiple and apply partial pivoting, even then we get wrong answers. So let's see what happens. We will look at the first column. Entries are 30 and 5.291. So 30 is of course the larger one among them. So look at the multiplier, which is 0.1764. Okay, this leads to the system. The first one doesn't change, and the second one becomes minus 104300x2, equivalent to minus 104400. It's the same system that we had obtained in the very first example, and therefore it has the same inaccurate solutions, which is x2 equal to 1.001 and x1 equivalent to or approximately equal to minus 10. That's a very bad thing that has happened. So therefore what we really need is scaled partial pivoting. So what does it mean? The point is that although this 30 is bigger than this, what we should look at is how big is 30 corresponding to the remaining entries in the same row. That's what we have to look at. So it's not enough to look at the maximum one in the columns. We have to look at how far does this element behave compared to the other entries in the same row. So that is what is called scaled partial pivoting. So this is what we will have to do. And so what does it really mean is that it places the element in the pivot position that is largest relative to the entries in its row. So we will not just, because it's a matrix after all, you are making changes only by looking at a particular column, and then the similar mistakes can be made if you're not looking at which element has to be put first and which element has to be put second. Okay, so what we have to do is to find the scale factor SI for each row. Every row from first to nth, we will find this factor SI, and this is the maximum of mod Aij where j varies from 1 to n. So your I is now fixed. Until now we were varying I. First variable was varying and second was fixed. Now our first is fixed and second is varying. So we are looking at the ith row, and in the ith row we are looking at the element Si, which is the maximum among them. Assuming that this Si is positive, of course the Si is the maximum of the mod of entries in your row. If Si is 0, that would mean that maximum of the modulus entries are 0, which will mean that the modulus entries themselves are 0. But you cannot have a 0th row where some particular row being 0, because then the system will not be solvable. So we assume that our system is solvable. We assume that our matrix is invertible. Okay, and then so we assume that this Si is bigger than 0. Now the appropriate row interchange to place zeros in the first column is determined by choosing the least integer p with mod ap1 upon sp equal to the maximum of mod ak1 upon s1. What used to happen is that earlier we would just look at the ap1. We would not consider this scaling factor at all. We would look at that particular p which has the maximum of mod ap1 equal to what, we would look at that particular p which has that mod ap1 is the maximum of mod ak1. But here we have to change the set over which we are taking the maximum is not simply the entries in the first column, but the entry being divided by that scaling factor. And then we are looking at the one which has the maximum value with respect to all these things, and that one is being interchanged with E1. And then we follow the usual method. So the effect of scaling is to ensure that the largest element in each row has a relative magnitude of 1 before the comparison for row interchange is performed. This is what we will ensure by having done this. So in a similar manner, before eliminating the variable xi, where you will have ek minus mki ei, we select the smallest integer p such that mod api sp is the maximum of mod aki sk. Whatever we have done for I equal to 1, this will have to be done at each time. But now the good thing is that these SIs will not have to be computed every now and then. So these SIs will have to be computed per rows. We will not have to do it for each time you are changing the matrix. So row interchange will of course have to then done. So these computations, the scale factors will need to be computed only once at the start of the procedure. But of course, they depend on the row. So if your SI is corresponding to ith row, if you are interchanging the ith and pth row, then you have to interchange the SI and SP also. You can't keep the same scale factor and interchange the rows here. Then things will not get correct. So let's see the example that we had seen, which gave us a horribly wrong answer, whether our scaling helps in that. So what we would have is that S1, which is the first row, that has the scale S1 to be 591400. S2 is 6.130. That S2 doesn't change. And therefore, mod A11 S1 is 30 upon 591400, which is 0.50373 into 10 power minus 4. And for A21 upon S2, it is 0.8631. So we see that the second one has to be put in the first one, because by the scaling, the scaled partial pivot is bigger for the second row. So the interchange E1, E2 is made, and then you get the correct solutions. From here, we will get the correct results, x1 equal to 10 and x2 equal to 1. All right, so we have understood the Gaussian elimination method. The Gaussian elimination method works by eliminating the variables one by one. The ith variable being eliminated from the equations ei plus 1 onwards. We saw one method to do that when the pivots are non-zero. If the pivots are 0, one basic naive approach to modify the situation, to remedy the situation, would be to look at the next one which is non-zero and put it back in the 0th pivot. So you interchange those two rows. So that is one way, that is called partial pivoting. But this partial pivoting can give you wrong answers. So sorry, so that is just called pivoting, changing the pivots. But if your AKK is very small, then round off error will come, and therefore you have to apply the partial pivoting. But partial pivoting can also give you wrong answers because the scales are not considered. So we have to look at scaled partial pivoting, which will give you the correct answer in most of the cases. Okay, so now we have to look at the operation count. Earlier we had looked at only the Gaussian elimination method and we counted the operations involved in it. But now we have modified the method, we have made it more complicated. And so we need to count the number of operations required now. So the first additional computations required for scaled partial pivoting result. Sorry, let me read that sentence again. The first additional computations required for scaled partial pivoting result from the determination of the scale factors. Okay. So there are n minus 1 comparisons for each of the n rows. Okay. For a total of n into n minus 1 comparisons. There are n rows and n minus 1 comparisons. So there are n into n minus 1 comparisons. To determine the first correct interchange, n divisions will have to be performed, followed by n minus 1 comparisons. So the first interchange determination will add n divisions and n minus 1 comparisons. Comparisons simply mean that you are given two entries and you should see which one is smaller, which one is bigger. This is roughly equivalent to doing a subtraction and then checking whether you get positive or negative. So the scaling factors, they are computed only once. So the second step will not now require those divisions, but it requires the further n minus 1 divisions and n minus 2 comparisons. So we proceed in a similar manner until there are zeros below the main diagonal in all but the nth row. The final step requires that we perform two divisions and one comparison. So that's the final thing that we will have to do. So as a consequence, the scaled partial pivoting will add a total of these many comparisons. So this is 3 by 2, n into n minus 1. So it's a factor of n square. It's big O of n square. And summation k, which is n plus 1 by 2 minus 1, which is roughly again big O of n square. Divisions. These are the divisions. So the time required to perform a comparison is about the same, meaning you have to just do a subtraction and then notice whether you get a positive or a negative number. That's the only thing you have to do. So this is roughly considered to be the same as the addition and subtraction. And therefore the comparison operations will now be added to the addition subtraction operations. So the total time to perform the basic Gaussian elimination method is big O of n cube by 3. These many multiplications and divisions, and again these many subtractions and additions. Here, the scaled partial pivoting will not add significantly to the computational time required to solve a system for a very large system, for a very large value. And that is because this is big O of n square. Both of these are big O of n square. So compared to n cube, the n square will not make a big change. And the important thing here is that we have chosen the scale factors only once. That is a very important thing, because if you were to do it in a method where the scale factors are changing every time, you have to determine the scale factors every time, then n into n minus 1, which was the number earlier, comparisons, that would be replaced by summation k minus 1. Because earlier you have n minus 1, next term would be n minus 1, n minus 2, and so on. And this makes a significant change. It is roughly again n cube by 3, big O of n cube by 3. And so as a consequence, this pivoting technique would add big O of n cube by 3 comparisons in addition to the n plus 1 by 2 minus 1 divisions. So the number of divisions that is being added is still big O of n square, but the number of comparisons which are being added, which is the number of additions or subtractions, that is going to be quite different if we were to apply the computations of scale factors at each time, but luckily that's not the case. So the scaled partial pivoting method does not change the computation time significantly for large values of n. Okay, so this is about Gaussian elimination method. We have learned the method and we have also seen various modifications to the method. We will now go towards the factorizations of the matrix that we obtain using the Gaussian elimination method. So we begin that from our next lecture. We will stop here. Thank you and see you again.